today. Thanks for joining us. If you are here, it means that you'd like to know more about the lab in a box. This short video talks about teaching from a lab in a box. My name is Moses Oyeku. I'm a Master of Philosophy student in the School of Engineering at Western Sydney University. Thanks for joining us. Well, first of all, what is lab in a box? A lab in a box is a complete home laboratory kit that enables students perform electronics experiments and also participate in practical classes remotely in the laboratory. The lab in a box extends the teaching of electrical and electronic concepts beyond the traditional four walls of the laboratory. So this home take-up kit empowers the student to do much more than they would normally do inside the lab class. Before we go further to talk about the lab in a box proper, I wanted to talk about two pedagogical models that you may be familiar with. First of all, the traditional classroom model. In this model, the student takes their tutorials, lectures, and performs their labs in the lab classes on campus. And then when they're at home, they solve problems and do the assignments until the next class on campus. What about the other model, the flipped or inverted model? Well, it's called flipped because the components are flipped, so to say. So the traditional lectures that you have in class is now recorded, uh, and they're also accessible on Zoom. The tutorials are also pre-recorded and it's also live on Zoom. The students don't have to attend the class in person on campus. The same goes for the lab, and this is where the lab in a box comes in because the student is able to perform their lab experiments outside the four walls of the laboratory. So, what do they do while they're in class? Well, this leaves the time to talk about the problems or challenges, or pretty much discuss with their peers about what they're doing, get ideas from others, and build on that. So, the student really is guided on what to do in the class. But the first, they have to try out, they have to experiment on their own outside of class. And that is why it's called the flipped and inverted model. The lab in a box, as we mentioned, is administered in a flip model, but also as a in a blended mode. So students can come to class, but they can also do their lab classes at home. Alright, so more about the traditional lab setup. In the video there, you see students as they normally would come to class and we have the setup. The setup for electronic lab classes usually involves having a power supply, function generator, oscilloscope, and a multimeter. The entire setup usually costs about $11,000. That's excluding any other equipment that they may have present. What are the functions of this equipment? Well, to put it simply, uh, most circuits need a power supply. Uh, any electrical component, any device would need a power supply. So that's the power supply unit, usually DC values. Then you have an input, and that is where the function generator comes in, or arbitrary waveform generator. So it generates a signal into the circuit that's built, and then the output or the response to the signal is can then be visualized on the oscilloscope, and that is how these three work together. Generate power, put in an input signal, and then see how your circuit reacts to the signal. The multimeter there is for taking readings, voltage, current, resistance, capacitance, just minute, you know, really localize currents and values across each of the components. So let's move then to the next slide, but just have an idea of the price of a traditional student setup. Now, using lab in a box in a flipped, guided, and exploratory mode, you have a student there performing her lab class at home. She's performing their lab class at home. What are the contents of the version 1 of Lab in a Box, the one we have so far? You can see them there. Jumper wires, the multimeter, breadboard, wire strippers, an Arduino components, and shield USB cables, LEDs, switches. I want to talk briefly about the Arduino there. It's An Arduino is a microcontroller used to build digital circuits, analog ones as well, but this microcontroller and the software is used to build circuits. So it really empowers the student to build slightly complex circuits, and this is why the lab in a box is so beautiful, because the students can do more than they can assemble more than just basic circuits. So all of these components go into the lab in a box on the right there. So remember we talked about this for equipment. Yes, so we have the Espotec Labrador board. This board is one of the items in the lab in a box. It helps the students perform the basic functions of all these four equipment here. Supplies power to the circuit that they've built, generates an input signal into the circuit, and helps the student to visualize the response or the performance of their circuit in response to the input signal that has been received. It costs just $39. Wow. It's not this particular Labrador board gets the job done. It's a simple circuit or simple item, I should say. It's not complex. It can't do everything, but it gets the job done. Earlier, I talked about online content. Well, yes, um, a lot has gone into making instructional videos, recording lab tracks, demonstrations. Some of these content will be available in the description of the YouTube video that that's accessible to you. Feel free to have a look at some of the videos that have been made to assist the students. Well, now here we have just a list of the items in the lab in a box. I forgot to mention that they are also prefabricated assemblies. So there are some components that were pre-made by the technical officers in the university, um, and that will be specific to the actual subjects that the students are using the lab in a box for. So how do the students use the lab in a box? Well, the very first thing to do is to design the circuit using Multisim. Multisim is a free circuit design software. So the students design their circuits for the project. For example, this is a differential amplifier. This version, this is an instrumentation amplifier. The students design the circuits, and as you can see clearly there, the 50 millivolts 1000 hertz signal there is the input signal from a function generator. The students design the circuits. The little round V's there indicate the oscilloscope. That's the where they would read out the response of the circuit to the input, for example. So the students designed this in Multisim, they test it, and if they are happy, they move on to the next stage, and that involves designing the circuit using the components indicated here. For example, resistors, op amps, capacitors, all here. The components are in the lab in a box, and they design them. The very next step will be Tinkercad. The students use Tinkercad. Tinkercad is a 3D modeling software used to design the circuit as they would using real components. As you can see here, this is the 3D representation of the circuit. Op amps, resistors, all here. To test the circuit, make sure that it doesn't blow. The circuit performs as it should. The resistors do not fail, and all the components do not fail as well. And if they are happy, they can then move on to design the real circuit using the components in the lab notebooks. So we have here the final stage where the students builds the circuit as it would look like in the Tinkercad circuit, connect to the Espotec Labrador board, and then connect that using the provided USB to their computer where they visualize what? The actual circuit, the oscilloscope, as they would on an oscilloscope. You see there, this is an instrumentation amplifier. The student is able to visualize the output of the instrumentation amplifier. So what we see on the right there is what we would see on an oscilloscope, and that is the last V in the circuit, which shows the output from the instrumentation amplifier. Well, this video is also available online. It's just a demonstration of how an online track would go. This is a session where the academic staff is taking a tutorial and is assessing the students' work. I'll briefly run through the video.
Good morning, everybody, and thanks for joining this class on the instrumentation amplifier. So I trust that you guys have assembled a breadboard with your instrumentation amplifier as you see it here. Okay, let me just assess your assembly. Okay, Felipe, that's great. Moses, that's great. Oh, it's very tidy. Good job, guys. Now we just have to see if it works. So who doesn't want to start? Felipe?
Sure. Yeah, sure. I'm going to share my screen now.
Okay.
Okay, we'll move on to the second student first. Then
Switch to Moses to do the same.
Okay.
Let me just move it. Yep. Okay, I can see your breadboard there and your Labrador board. Yeah, also your assembly look very tidy. So if you want, you can start sharing your Labrador board output. So like Felipe, have you removed the gain resistor to do a gain of 1? Oh, that's perfect. So that is the same kind of measurement I have shown into the demo.
Correct.
So then that means that in your case, we don't need to debug anything, and I'm just looking forward to see your lab report with the measurement of the differential gain and the common mode gain and also of the common mode rejection ratio.
good. Let's stop there now. That's a quick demo to see how an academic staff will really troubleshoot with the students who has any problems, assess the students' work, the students demonstrate what they've done. All this is possible using the lab in a box. And may I add, they would do this in a traditional lab setup as well. Uh, but very innovative and enjoy the other videos that have been provided. So, how much progress have we made? Well, since 2020, um, teaching of these units have moved online, fully online. Uh, Practicals continued online, remotely. Even some students from overseas were able to, you know, perform practicals. They were not left out. So it's really amazing what has been done in the last few years. Would like to present very soon a case study on cost savings using the lab in a box. Well, of course, the question is, well, are we saying that we do not need to go to labs? Well, we're not saying that. We're just saying a lot can be done to prepare the students before they actually come to the lab, and really makes it flexible so that students can learn, and then when they come to class they can do a lot more. Questionnaires and surveys have been administered, they're in progress, and we are working on Lab in a Box 2.0. So please watch this space. Exciting times ahead. I want to say thank you to everyone who has really helped out on this project. My supervisors, particularly, they've been very good, they've been very patient, and technical officers as well. I also like to thank you too for taking the time to watch the video. Thanks for your time.